We are Group 2. We're going to talk about mathematical modeling and applications of PID controllers.
My name is Wang Jianwen, and I would like to talk about the role of control system and the importance of PID control in electrical engineering. What is a control system? A control system is a machine that automatically adjusts a system's output to match a desired input or target. Even when distribution occurs, it works to keep the system stable and accurate. You can find control systems almost everywhere. In automatic factories, electric vehicle, air conditioning system, and even drone stabilizer. Why are control systems important? Control systems are essential for ensuring safe, efficient, and stable operation across all areas of engineering. They are fundamental of automation and intelligent systems, powering major industries like transportation, manufacturing, energy, aerospace, and healthcare. Now, let's talk about PID control. PID stands for proportional integral and derivative control. This strategy was first used in the early 20th centuries for ship steering. Later, in the 1940s, Baker and Nichols introduced a system tuning method that made PID much easier to apply in industrial settings. Even though it is a decades-old method, PID control is still one of the most widely used techniques today, implemented in over 90% of industrial control systems. It's commonly used for temperature, speed, and pressure control across many different fields. Why is PID still so popular? There are three main reasons. Simplicity. It's easy to understand and implement. Stability. It provides reliable and consistent performance. Flexibility. It works well for continuous systems like temperature, pressure, or motor speed control. Conclusion. In summary, control systems are truly at the core of modern engineering. Among many control strategies available today, PID control remains one of the most practical and efficient. Successfully connect theoretical design with real-world results, and even as advanced technologies like AI and model-based control continue to evolve, PID still plays an irreplaceable role in many everyday systems.
Now, let's talk about what a PID controller is. A PID controller is a control loop mechanism that consists of three components: P for proportional, I for integral, and D for derivative. Each component contributes differently to the control output. Before we discuss the control function, I need to introduce an important variable. This variable represents the error at time t, which is the difference between the desired value and the actual output. This error serves as the input to the PID control function. Now, let's take a look at the functions of PID controller. As we just mentioned, it consists of three components: proportional, integral, and derivative. These three terms work together to determine the controller output U based on the error at time t. The constants Kp, Ki, and Kd are the non-negative coefficients for the proportional, integral, and derivative terms, respectively. The first component, proportional, is the product of error and the coefficient Kp. When error is small, the output is also small, meaning that as the system gets closer to the desired value, the response becomes less intense. Conversely, when the error is large, the output increases, which helps the system approach the target more quickly. This graph shows how the output changes by the control of proportional terms. Starting from t equal to 0, the output continuously moves toward the target value. As it gets closer, oscillations occur, and eventually, the output stabilizes and approaches a certain value. However, there is still a gap between the final result and the target. This gap is known as the steady-state error. It is caused by the environmental factors that shift the system's equilibrium away from the target. So how can we eliminate steady-state errors? This is where the integral components come in. This term integrates the error over time and multiplies it by the coefficient Ki. As long as the error exists, the integral term continuously to accumulate until the error becomes 0. As shown in the diagram, at the time t0, the error is greater than 0, so the output increases. By the time it reaches T1, the error becomes 0. The output stops changing. Looking at the graph again, when both the proportional and the integral components are used together, the system is able to eliminate the error as it approaches to the target, thanks to the effect of the integral terms. This allows the final output to converge to the target value. The final component is derivative. This term calculates the rate of change of the error to adjust the output, helping to prevent sudden change and reduce oscillations as the system approaches to the target. With the combinations of proportional and integral, the output can reach a steady state. However, if a sudden and significant change occurs that causes the output to deviate from the target, the derivative component responds by pulling the output back toward the target. As the system gets closer to the target, the derivative effects gradually decrease, eventually bringing the output back to the desired value. This animation shows how the output changes as the proportional, integrals, and derivative components are added. The final result also demonstrates how PID effectively controls the output.
Here are the applications of PID control systems. 1. Industrial temperature control. In manufacturing processes like plastic molding or food production, precise temperature control is essential. A PID controller adjusts heating levels based on temperature errors, keeping the system stable and ensuring consistent product quality. Second, motor speed control in automation. In automated systems like conveyor belts or robotic arms, motor speed must be accurate and responsive. PID controllers help maintain the desired speed, quickly compensating for low change or disturbance. Third, direction and speed control in autonomous vehicles. Autonomous vehicles use PID controllers to follow lanes and manage speed. One PID loop adjusts the steering based on lane deviation, while another ensures smooth acceleration and braking.
Has a number we can check. E is for speed and reaction. I is for fixing small errors. D is for smooth movement. We can make the numbers bigger or smaller to see how the machine changes. We try different numbers until the machine works best. Let's see what each part does when we change it. Proportional makes the machine move faster. Too high equal too much shaking. I interval makes the machine start at the right place. Too high equal moves too much or slowly. The derivative makes the machine smooth and calm. Too high equal can make the machine slow or noisy. So change PID helps the machine be faster, smaller, or more correct. We must be careful. Too high or too low is not good. We change PID in a smart order. First, change P. Make the machine move, but not shake too much. Next, add I. Help the machine stop at the right place. Let's add D. Make the movement smooth, but not jumpy. This way, the machine becomes fast, correct, and calm. We test again and again to find the best numbers. P helps it move. I helps it start right. D helps it stay smooth. We adjust the numbers step by step to make the machine work just right.
Now I'm going to share our conclusion. First is how engineering mathematics and control systems work together. While doing this report, I learned a lot. Before, when I studied engineering math, I often felt that the formulas didn't have much to do with real life. I thought we were just solving problems in class. But after learning about PID controllers, I saw that math is very useful in real systems. Things like differentiation, integration, and Laplace transforms help us understand how a system works and how to make it better. The P, I, and D parts of the controller are really ways to use math to improve system performance. After this project, I feel that engineering math is more important than I thought, and I will try to see its meaning more clearly in future learning. And I want to talk about the future. After finishing this report, I also thought about how control systems can be used in the future. As technology grows fast, in things like self-driving cars and smart factories, better control methods will be needed. PID controllers still work well, but in some harder situations, new ideas like AI or adaptive control might be better. I don't know much about these yet, but now I am interested to learn more. I also noticed that I still need to improve my math skills, so I can better solve real engineering problems in the future.